Hello, hello, hello. Welcome back to our bi-weekly review session series. This is review session number 4. Today we're going to be focusing on BSTs, hash sets, and sorting. So this is our last review session before the final exam review session, which is going to be a big event. Keep an eye out for that. It's going to be on April 12th. But before we get started today, can everybody just take the time out to sign in with the QR code? It's going to go on your Laurier experience record. It might even count for a speaker series if you guys are enrolled in co-op. Yeah, sign up for all that good stuff. I'll leave it up here for like 30 seconds and then I'll get started. So it's only going to be me and Mila today. Kind of a weird switch up. Last week or 2 weeks ago it was only me and Noah, but Noah's feeling under the weather. He has Inya, so yeah, if anybody else needs it, just type in the chat. But if not, I guess we can just get started. Okay, so we're just going to look at our roadmap like we do every review session. So this is review session 4, like I said. It's going to be our final penultimate review session before our final review, which is going to be an in-person event. Everybody can come out to that. Free food. You guys can answer questions. Or not answer them, but ask them rather. We're probably going to have a final exam, practice final exam to give out to everybody, which should be helpful. We're going to have Kahoot for prizes. So make sure everybody has April 12th crossed off their calendar as CP164 final review session date. So let's jump right in. So first thing we're going to be talking about is binary search trees. What are they and what are their common use cases? So what is a binary search tree? So binary search trees are rooted tree data structures that organize data depending on a key value. So what does that mean? So what this means is BSTs are linked data structures that are represented as a head or a root in the data structure, and every other value or key is linked to them using a left and a right. So this is something we call a non-linear linked data structure. Before we were looking at, for example, linked lists, linked stacks, linked queues. Those are all linear because they only go one way, either front or back. With a doubly linked list, for example, we can go back. But if we have a next, that's only linearly linked. But this one, as we can see here, the left subtree of a node contains only nodes with keys lesser than the node's key. So we have a left subtree and a right subtree, or we don't even need a tree. We can just have a parent node at the top here and then a left node, and we don't even need to have a right node or a right node and not even a left node. But usually we only have 2 maximum children, so it's only going to be left and right. The right subtree contains only nodes with keys greater than the node's key, so the node being the parent key. So everything on the right of the parent is going to be greater than it, and everything on the left is going to be less than it. So left, and something we also need to remember is that left and right subtrees are also binary search trees. And this is very important when we start learning about the types of algorithms we can do with binary search trees. So let's look at this example really quickly. I always feel that when you see a data structure, especially one that isn't linear, it's a lot easier to kind of visualize what kind of code you need to perform to either traverse, insert, or remove from it. And that's very important because in a binary search tree, the whole point is to have insertion and removal that's more efficient than a different data structure, for example. So as we can see here, our parent or our root or our head, whatever you want to call it, is 8 right here. So from 8, everything on the left of 8 we expect to be less than it, and everything on the right we expect to be more than it. So as we can see here, 8, its left child is 3 and its right child is 10. As we can see, still follows the BST rules. And then we get to this 1 from the 3. So what we call this 1 node is a leaf node. A leaf node pretty much is just a node that doesn't have either a left or a right child. And this is going to be mostly our base case whenever we run algorithms to find this. And that kind of leads me to my next point is the way we traverse through binary search trees is always going to be using recursion. since it isn't linear, we don't know how many levels it goes down. So we can't really use anything other than recursion. We can use iteration, like with for loops and whatnot. It just doesn't make as much sense in this context because we always want to kind of split left and right. And if you think about it, if this were to have all of these nodes that are currently on the screen with like left and right children, so no leaves except for the ones obviously on the bottom row. If you think about it, we have one node up here that splits into two. That two would then split into four, and then that four would split into eight. So it just keeps going larger and larger down. So the recursion really helps us deal with the ever-growing tree. And yeah, pretty much that's how a binary search tree will always look. And we don't have to make any modifications after we insert it. So let's take a look at the insertion actually before I start speaking about it. Because our insertion will automatically place the value where it's supposed to be. So some other data structures, such as a heap or a priority queue, we can have it so that once we insert, it just puts it at the end, and then once we delete, it sorts after that. But with a BST, we insert into the correct position first. So let's look at how this data structure is implemented and just the insertion function really quick. We don't have the removal function here. We kind of left it as an exercise to you, but it's the exact same way as the insertion function. So let's look at it here. So we have a BST node, and this is each node like we saw before. It has a value, so that's whatever, like 3, 8, 10, whatever those values were, the number. And then it has a left value, which is set to none to start, and then a right value, which is also set to none. And then this is not necessary, but it's just for ease of use for the user. We have a BST class, and we just have the root as a none, and then the count, which is just how many nodes are within this tree. So as we said before, our insert is going to be a recursive function. So we have an insert here that calls an insertion auxiliary function. So this aux function is going to be the recursive function, and this one is just going to be calling it. So we go first to our base case. If node is none, so if we don't have a node being passed to the tree, we just want to say that node equals BST node of value. So we're creating a new node, and our head or our tree now becomes that node, and we can say self.count plus equals 1. And we also want to return an inserted, again, just for ease of use to check whether we inserted or didn't insert a value. And in this case, we inserted true, just because there may be. So in this BST, we don't want to have duplicates. That's just something we don't want to have, just because it's going to kind of violate the rules of the BST. We want it to be less than or greater than, no equal to. That's not a case we have. And that's why we have this inserted equals true or inserted equals false. So then we have elif node dot underscore value. So if the current node that we're on has a value greater than our value, then we go to the left subtree. If you see here, node dot left equals self dot insert node on node dot left. So we want our left subtree. We want to traverse through our left subtree to find where we want to insert it, because our value is smaller than our current value, because we know everything that's smaller than our parent value is going to be on the left of it. And then the opposite way we go, elif node value is less than value, then we call the function again on node on the right subtree. And then we just check if inserted. So we were checking if inserted is true, then we just update the height. This is just another function that you can implement later, which doesn't really matter. Or we could also do self count plus equals 1. So that's fine. This height is a different, it's how many levels there are. Sorry about that. But this is also, again, not necessary for the insertion. It just makes it easy for other functions that we may use on the BST. So that's pretty much what there is to BST. So they're non-linear data structures that we use recursive functions for insertion and deletion. And actually, before we move on, we need to see what the time complexity of this is. And this is a very important point in a binary search tree, is that we know that every time we pass, every time we don't find an insertion point for our value, we're splitting the input that we pass on to the next in half. So if you think about it, when we don't find it here, we're saying no dot left. So we're assuming that node left and node right are exactly equal, just for ease. And so we know that if we go to node left, we're now scanning only half as many nodes as we were before. So we know from previously in our review sessions and previously in course content as well, that when a algorithm splits our it splits our input by 2 or more, then we call this function a worst case of log n. The math is kind of complicated on it, but just think about it as every time we go through a function, we're splitting it in half. So we're never going through the entire function's input, because we don't have to, if we know the value is less than a certain point, we only have to look at the right subtree or the left subtree, whichever one. We don't have to look through the rest at all. We can just completely disregard it. So it can't be O of n, so it has to be the one smaller than it, O log of n. So just remember that, and this is why BSTs are important, because we can insert and remove faster than an array, for example. If we have an array, the only insertion that is not O of n would be adding to the end, because once we add to the end, we don't have to move any data back. But let's say, or removal, sorry, but adding as well, we have to shift data over and shift data back. But if we add to the end, again, it's going to be constant time, because we're just adding to the end, we don't move any data. But let's say we want to add in the middle of an array, we have to take all of the data on the right and shift it over one place. And worst case is adding to the front. So insertion in an array would be O of n time, but insertion in a BST is always going to be O log of n at its worst case. So we know that BSTs are very important because they're more efficient at insertion and removal than other data structures. Okay, so let's move on to something as well that's also very efficient at insertion and removal, a hash set. So what are hash sets? A hash table is a data structure that contains an array of fixed size called a table. Each position in the table is called a slot or a bucket, and the size of a hash set, which is actually the size of the table, is its capacity. To insert into a hash table, the key must be mapped into an integer via hashing to compute a unique index. So what do we mean by this? Let's just go to this really quick. So as we can see in the implementation, we have a hash function here. And what this hash function does is we're just taking a movie title, and for each letter in the movie title, we are converting that. This ORD function converts a character into an integer. So it's just the 0 through 26 for lowercase, and then 27 through whatever for uppercase. And then we are creating a unique index for each title. So if you think about it, we're kind of creating a key that maps to an index for every title in the movie. So collisions and rehashing. So obviously, if we were to have a function, it's not always going to be perfect. We can have duplicates. So this is what we call a collision. Collisions occur when duplicate hash numbers are generated and are attempted to be inserted into the same slot in the hash table. So one method we can use to solve collisions is something called separate chaining. Each slot in the hash table points to a data structure, a different data structure, example a list, sorted list, or binary search tree, to store multiple data elements that hash to the same slots in the table. The resulting hash table is referred to as a chained hash table. Or we can have something else called rehashing. So this is used to increase the number of available slots instead of continuing to grow the lists attached to the slots. It's decided depending on the load factor. And so what is the load factor? Load factor is just a constant that we use for each hash table to know when we have to rehash. So the rehashing algorithm is pretty simple. First, a new table is created, which has a capacity larger than that of the original table. Then all of the data elements in the hash table must have their indexes recalculated and moved to a new slot. So let's see how this is kind of done. So we have a hash table here being created. So our capacity is equal to the capacity that's being passed, and then the table is just equal to an empty list. In other languages where lists aren't dynamic, we have to define how much space that is, and we also have a count. So then we define the empty table. Obviously, that's what we're doing here. And so whenever we want to input into that table, we just use this hash value, or this hash function here rather, to give us a unique value of each title in a movie in this instance. And so when we do hit a collision, we can create a hash table that is greater in size than whatever we did before and pretty much carry out the same exact method. So this is a hash table that's being created on our own volition. There's another thing that is a hash table, or rather a hash map. They're very similar, but it's already a data structure within Python, and it's called a dictionary. And this is a built-in data structure. I'm sure you've all used it before, or at least heard of it. So what this does is it's the same thing as a hash table as if we were to implement it by ourselves in Python, except it's implemented already within Python. It's built in. So what it does is it has a key and a value pair. And this is very much the same, except they do the hashing kind of behind the scenes. So all we see when we're using a dictionary is the key and the value. And so the same way that this hash is O of 1 insertion and O of 1 deletion, because all we have to do to insert is create a hash, and then we put it in that index. And then deletion, we do the opposite. We take the opposite of the hash, and then we return that. For a hash, for a dictionary, sorry, it's the same exact way. It's hashed as well, but on the surface, it doesn't show that it is. So it just kind of shows as a key value pair. So yeah, if you are to use a hash table, or you want to use a hash table but you don't want to implement it, just go with dictionaries. They're data structures that do the exact same thing. They're both extremely fast in insertion and deletion. And yeah, they're both pretty much called hash tables. And in other languages, a dictionary is called a hash table or a hash map. So if you've ever heard of that term before, this is where it comes from. And yeah, so let's move on to sorting algorithms. Mila's going to take us through that.
Hello. Okay, so let's go into our sorting algorithm. So we're going to just cover the different types and their time complexities, and just kind of big O in general. So types of sorts. So you guys are learning right now, there's two different types. There's comparison and there's non-comparison sorts. So basically the main idea, self-explanatory, algorithms in comparison sorts, so there are algorithms that work by comparing the keys of data elements to find the desired order. So you're basically just, comparing the values between each element, and then that's how you figure out how you're supposed to sort it. So these examples include insertion sort, which we're going to take a look at, selection sort, merge sort, and quick sort. And then we also have our non-comparison sorts, which are algorithms that make assumptions about the input array size, and so therefore they can run on linear time. And so what this basically kind of means is that there are no comparisons between values that occur. Instead, the algorithm relies more on integer arithmetic on keys, and so there's no comparator. It's only just arithmetic on keys. That's how it's sorted. And so examples of this include counting sort, radix sort, and I believe there's also like bucket sort also part of this. So we're going to take a look at radix sort. So let's move on to our example. So we have insertion sort. So the main kind of idea of this sort is to always compare with the left value and then sort towards the right. So here we're starting at the index 1 and not the first element, because why? There's nothing to compare to on the left if we were to start with the first element. So we're going to start with the second element. And so J is holding the index of the previous element, which in this case we're starting, so 0. And so what we're basically trying to do in this loop is we're saying that while the index j, and the next, so yeah, while the index j is greater than or equal to 0, and the next element, so that would be our key, the next element is less than the previous element. Then, if that's the case, right, I said that right. Yeah, we're saying, yeah, next element is less than the previous element. Then we're saying that we want to move the previous element forward, right? And so this then creates an ascending order when we fully loop through, because what we're doing is we're going to constantly, okay, and yeah, also when we decrement, we're decrementing j by 1 so that we can compare with the other left elements, because the whole point of the algorithm, right, is so that we start here, we compare, and then we move on, and then we compare. We always want to compare with the left. You're always moving one ahead, if that makes sense. And then you are always like sorting towards the right. And so then you create this kind of ascending order. And then, yeah, so like, for example, if you had like 5, 4, 7, 2, right? When you get to 2, you need to compare that. So as the comparison would go through, it'd switch. It would go like 4, 5, right? And then we have 5, 7. So 5 is still less, so that's fine where it is. And then we have like 7, 2. But then you see that 7, and so 7's here, 2 is here. These need to be, switched, right? And then we also have to decrement because we also have to look at the previous ones. We know we have 4, 5. We know that 2 is less than all of those, so it's got to be pushed all the way to the front. So yeah, that's kind of the main idea how it works. I guess just the main thing to note about this algorithm is that you're always sorting, you're always not sorting, you're always comparing with the left, right? And then that's how you sort, and then it creates your ascending order. So yeah, that's insertion sort. I'm sure you guys are probably already familiar with it. So let's move on to the next one. This one, I believe you also have to like implement it in one of your either assignments or so, but yeah, so this one's pretty important. I would definitely say understand this well. So rate XOR. So how does this work? So this is our, like we said before, our non-comparison sort. So this is based off of arithmetic, integer arithmetic. So how our kind of, program is working here is, so the way I did this, I did it like this. You guys obviously can like write it a completely different way. It doesn't really matter, but it's always the same idea, right? So I created this kind of M bucket. I call it like a master bucket, and there's 10 elements inside specifically. Why? Because integers 0 to 9. And so what we're kind of doing here is, yeah, so this top code, these two for loops are basically just creating, the bucket. And so this is kind of the main important part, is inside this entire if statement. So what we're doing first is we're finding the max element, or the max number in our input array. And so what we're doing with that is we're finding, so I'm converting it here to a string just because I want to find the length. So what I'm basically doing here, the length is the number of digits in the highest number. That's how many times we're going to do the overall loop for, right? And so yeah, you can see here in the for loop, that's how many times we're going to loop. It's all based off of the number of digits in the max number. And so what we're doing here, so our I signifying our list position. And so what we're saying, so while I less than the length, while we're not hitting the end of the list, we're going to grab that element number. And so what we're doing here in this B index essentially is we're computing the corresponding index to put into the master bucket. So I don't know if I should really like go through this. Like I remember I did this and it works. But that's kind of like, that's the main idea. Like that's what it does, is it puts it, you're trying to basically like order everything into these buckets into the main one. And because at the end, what we're going to do is we're going to pop those all, and they're going to all be in order, right? And so, yeah, so here, this bucket, it's the linked list inside, and then we're going to be appending our number there. And then, yeah, we're going to increment, and we're just going to keep going through and then filling these buckets essentially. And that's how we're going to get our end order. And then here at the bottom, we just have empty our list and empty out all the buckets. So the way that you empty them, that's the way that they'll be in order. So it's kind of systematically done. But yeah, that's kind of the main thing. I would definitely, put emphasis on this sort, know it well, know all the sorts well, but yeah, I think this one, it can definitely be a pretty tricky one. So yeah, that's the breakdown of radix sort. So let's go and take a look at time complexity. Okay, so this is my little table that I made. And so it's kind of just goes through like each and every, notation that you guys have probably already covered or you will cover. And so it's honestly like, I feel like this was like literally my little cheat sheet, if you want to call it. Like this is how I knew how to do the big O stuff. So O of 1, this is how just I remembered it by just simple if statements, so no recursive calls or no loops. So this is a constant time complexity. As the size of our data increases, execution time stays the same. So some examples anywhere where it's like if else, if that's like the only thing inside of your program. And other examples include inserting a node into a linked list, pushing and popping on a stack, insertion and removal from a queue. So pretty simple. O of n. So this is how I remembered it by a single loop or recursive call or consecutive loops and recursive calls of the same type. This is linear time complexity. So amount of data left after the first iteration is n minus 1. And so some examples of this include the bucket sort, the radix sort, deletion in a linked list, traversing an array or linked list, and comparing two strings. I would definitely say it's important, know for each of the notations where like examples of such, not just like what they do, but like where can you actually like see it inside of your code. Like if you, just to practice, I guess, even for like the final or anything, just, go through your Simon's labs, whatever, and like identify where is like what time complexity occurs where. So then we have O log n. So amount of data left after the first iteration is divided by 2. So like Stephen was saying before, we've got our binary search. So yeah, here we have n divided by k, or yeah, divided by k. Binary search works like n divided by 2, but yeah. So logarithmic time complexity. And then here, just like a little note, I guess, happens normally with single loop or recursive call, but I don't think that's always the case, but in most cases. Then we have O(n) squared. So here we've got our nested loops or nested recursive calls. And then I put in capitals here is you have to examine them separately. Obviously, like there could be like if you have, another loop inside or something like that, like it'll change the complexity. So examine them separately. If you, or for example, I guess I could say like if you have a loop and then you have another loop that's nested, that's n2, right? Because the nested loop will take higher priority over the one that isn't nested. So then we have quadratic time complexity when both loops or recursive calls are linear. So examples of this include bubble sort, insertion sort, selection, comb sort, shell sort, and like you guys have probably already been given implementations for those, I believe. But yeah, and then finally we have O(n) log n. So nested loops where one O of n is inside an O log of n, or O log of n inside O of n. So this here, I don't really know if you guys have to know this, but in case of anything, like we can just go through it. So the amount of data left is n divided by k. However, both halves are iterated through and combined. So here I have in quotes, it's basically our divide and conquer approach. And then, sorry, what was I saying? Yeah, divide and conquer approach. And then our examples here are merge sort, quick sort, and heap sort. So yeah, that's kind of the breakdown of the time complexities. You guys obviously don't have to use this just for like sorting, but like this is, like I said, like go through your, assignment or lab or whatever, and then try and figure out where they can occur. It can be like, for example, like this inserting a node into linked list. So yeah, definitely very important to know these. And yeah, I guess that covers our topics for this review session. I'm going to hand it back off to Steven to finish it off.
All right, Kahoot. So I don't know how many people are gonna join, but here's the link. Let me make my face a bit smaller so anybody who can scan the QR code will scan the QR code. But yeah, join up, guys. All right, there's one more person in chat who's not in, so we'll wait for them. And people who are watching along in the VOD, make sure you don't skip through the Kahoot. I think it's pretty important to, I don't know, just test your knowledge a little bit. Okay, nice. I think that's kind of everyone. So what is the time complexity of insertion sort? Yeah, so it's O of n squared, and a lot of people got it right, but I guess the one person that got it wrong. The reason it is O of n squared is because we have to go through every single element within a list, and then we also have to compare that element with the rest of the list. So if you think about it, we're going through the list n times for every n elements. So that would make it n squared. So good job. So BST nodes have a left child with a greater value and a right child with a lesser value. Correct. Okay, nice. So yeah, BSTs have a right child that's greater and a left child that is lesser. So what determines when a hash set should rehash? So yeah, whenever the load factor is reached, then we know that we have to rehash our table. Obviously, we could run into rehashing before, but once we get to our load factor, it's good practice to hash. So a hash table is a data structure that contains A/n blank with fixed size called a table. So what data structure, pretty much, are we implementing a hash table with? So that's correct, an array. Because we want to be able to find an index where we can insert a value, and an array is the best way to do that efficiently. So which sort is not a real sort? So all of these are correct except for one. Well done, everyone. Yeah, Chesterfield sort is not a real sort. So good job. So why are binary search trees called binary? Yes, correct. So each parent node splits into two child nodes. So if we think about it, binary meaning 2, 0, and 1. So that's why they're called binary. Even though they do have no cycles, this is another characteristic of binary trees that we have to keep in mind of. They're trees, or every tree doesn't have a cycle, but they're not the reason why binary search trees are binary. Yeah, and I don't know if they fit societal gender norms, but that's for them to decide, I guess. So what is the time complexity of searching for a value in a binary search tree? Yeah, so to the person who answered O log of n, that is correct. So, as we said before, when we search for value in a binary search tree, we look at one. First, we look at the parent node. If our value is greater than the parent node, then we only look at the right side of the tree. If our value is less, then we only look at the left. And we continue to do this until we find where we want to be at. So, because of this, we're always splitting our input in half. Again, this is what the basics of a log n algorithm is. We're always splitting something in half, in three, regardless. But if you think about it, this is going to be a lot more efficient than O of n because we're only going to go through, we're not going to go through all of the solutions. We're going to go through way less than even half the solutions. Log n is minuscule compared to O of n. If you think about it, like what, log of 4,000 or 4 billion, let's say, it's still like 2,000 or something. I don't know the exact math. That might be completely wrong, but I know that log n is a lot smaller than O of n, and it makes sense because we're only looking through half of the values in every input that we're given. So just think about it like that. Every level we go down in the inputs, we're only looking at half of that, and that adds up a lot. N log of n is going to be greater than O of n, and so that's how we know that it's not that. And then O of n squared, we don't have to go through the entire tree for every single node. So that's why the correct answer is O log of n. So what's the time complexity of inserting a value in a binary search tree? So the last one was deletion, this one's insertion. Yeah, so again, they're the same. So every time we insert or delete, it's always going to be log n because of the nature of the binary search tree. It's sorted. And this is the same way with a sorted array. If we have a sorted array, we can have 2 pointers on either side. This is a binary search. This is the algorithm. We have 2 pointers on either side. We find the middle. If the middle is larger than our value, then we only search the right side. If the middle is less than our value, then we only search the left side. Or the other way rather, sorry. If the middle is smaller, we search the right side because our value is larger than the middle. If the middle is larger than our value, then we only search the left side. And through this, we can half our input every time. So we go half, and then again, we calculate the middle. We choose one side where we're at, half again, middle, half. And we do the same thing in a binary search tree, and that's why it's O log of n, time complexity. So what type of functions can hashing functions be? Yeah, so that's correct, the people that answered. Any function that returns a valid integer. So the purpose of hashing functions is to find an index. So mathematical operation may be correct, but that's not our most general terminology or general definition of a hashing function. The most general definition of a hashing function is a function that returns a valid integer, valid meaning within our accepted integer list of indexes. A mathematical operation on two integers could be the case, but not general. And any function that returns a string is incorrect because we want to return an integer always, because we want to return an index. So which is not a property of BST? So all of these are correct except for one. Yeah, so the correct answer is they can have cycles. This is not a property of BSTs, as we said before. Trees in general don't have cycles, and BSTs are no different. No nodes can connect to a node that will then connect back to that node. Each left and right subtree are also BSTs, and this contributes to that fact that we can split. Like, imagine our left and right subtrees weren't BSTs. In that case, we would have to search the entire tree before we can find our insertion point, because we don't know whether or not our proper insertion point is going to be on the left or the right, because they're not BSTs. So that wouldn't work. So they're both BSTs, the left and the right, and everything on the left is smaller and everything on the right is larger. So always keep that in mind when working with BSTs. Okay, so in third place, we have fish emoji. Well done. Second place, we have nickname. And in first place, drum roll, we have Jamaican me crazy man, the Jamaican emoji. I don't know if that was cultural appropriation. I hope it wasn't. I swear I wasn't trying to do anything wrong. But thanks for joining us today. Well done to the people that did good in the Kahoot. Everybody watching on the VOD, I hope you joined along for the Kahoot. My prediction for when the VOD comes out, let's see. In 1 day time, what's going to happen? Tomorrow, the stock market will open 8 points below today. Keep that in mind. If I'm right, everybody, my e-transfer is stephentome59@gmail.com. Send me all your money and I will make you billions. If I'm correct. Only if I'm correct. But also don't do that. It's against university policy and I'm just joking. This is just a joke. I'm just joking. But I'm not. So send me money if I'm correct tomorrow. 8 points below. Remember that. Okay. Good night, everybody. Join us. Laurier campus, not sure which room yet. April 12th for our final review session. It's going to be the best one of the year. So definitely do not miss out on that. And yeah, thank you all for joining us tonight.